All right, here's our video for basics of waves. So the introduction of waves, got a couple good memes here. Feel free to stop and look at them. I encourage you, have the PDF of this notes out and ready to go as you're going along, so you have that to follow with. Here we go. So types of waves. There's two main categories and types of waves that we'll look at. First is mechanical waves, and second is electromagnetic waves. So mechanical waves requires there to be some sort of transfer of energy through a medium of some sort. So the medium is what we call just any sort of matter that a wave has to travel through. So that's air, water, anything like that. Electromagnetic waves, they don't need a medium. They can pass through mediums, but they don't need one to operate. That's the difference here, because mechanical waves, they need a medium. They just cannot exist in a space without a medium. So that's why sound doesn't travel in space, because sound is a mechanical wave, and mechanical waves can't travel in the absence of stuff, which is space. Whereas electromagnetic waves can. That's why we feel sunlight, even though sunlight has to travel from the sun through space to us. So a mechanical wave, sound, water waves, things like that. Electromagnetic waves, they just transfer energy on their own. It's electric and magnetic fields that oscillate. And that's something that we're going to talk through a little bit more, what that means. But electric fields and magnetic fields, they oscillate through whatever kind of space it is. So example, visible light, X-rays, Wi-Fi and radio, things like that. Your phone operates off of radio waves. Wi-Fi operates off of radio waves. Your car radio operates off of radio waves, things like that. Okay, so mechanical waves, here's some more examples of it. Sound, right? This is a harp being played on the bottom left here. And in this harp, you can see that the medium of these waves is the harp string. Water, medium of the waves is water. Electromagnetic waves, you see a light bulb turning on, your phone screen, X-raying of a hand, radio waves being collected with data there on that satellite dish. The electromagnetic spectrum. So over on the left side is where we have short wavelengths. So short wavelengths. That means they happen often. So that is a high frequency because it happens often. High energy also. On the right side, opposite. So long wavelength, low frequency, low energy. I always like to do energy of a wave of how much energy would it take me to draw said wave. Like over here, oh, my marker, you can't even really see it. Over on the left side, I have to move very quickly back and forth. It takes me a lot of energy, whereas on the right side, it really doesn't take me a lot of energy to draw that wave. So that's kind of what I relate it to, because light always travels at the same speed, period, no matter what. But speed is always the same. So it's how much energy does it take me to draw that many squiggles as I'm moving at the same speed. All right. So a couple notes here. Amplitude. So that's how big the wave is. Amplitude right here, or let's say it was like this. Amplitude determines your brightness. The frequency, how often it happens, determines the color. And color is related to higher energies are purple, lower energies are red. And the higher energies, I like to remember that they're purple because what do you get burned by? Ultraviolet light. So if it has enough energy to burn us, then that means the violet is going to have enough energy. Whereas infrared light is just beyond the visible spectrum on the lower energy side, just past red. It has to be the other way because red is low energy. Purple is high energy there. Okay. The other thing, though, is light can be equally bright, which means the same amplitude, but brightness is not energy. There's different colors of LEDs that we've looked at. So there's red, green, and blue LEDs. Those are just the three colors that they make. A blue LED takes more energy to turn on than a red LED does. So you can have more red LEDs operating off the same battery than you can blue LEDs because of that amount of energy. Here is just something else to learn, to look at. AP does, unfortunately, make you memorize the order of these, and they make you memorize approximately what scale each of the waves is. So you're going to have to know the order of these, at least relatively speaking. So gamma rays are the highest energy, shortest wavelength. X rays are next. That's why you can only have so many X rays per year, is because they have enough energy. It's what we call ionizing radiation. And ions just means you've kicked an electron out. So ionizing radiation means it's got enough energy to kick an electron out of the atom. So that's X rays. So you can only have so many of those per year. If you ask your doctor for 20 or 30 X rays, they're going to say no. Gamma rays are even worse. That's what doesn't kill Hulk, but it should kill Hulk, is the gamma rays. Ultraviolet, it's got enough energy to burn you, so it'll cause mutations in your skin cells, but it's not really ionizing radiation. Visible light, that's what we're exposed to all the time. Infrared, so ultraviolet, visible light is next. Ooh, don't need to cross that out. Visible light's next. Infrared is next after that. And this graphic, it actually forgets one. It forgets one in here. And it forgets microwaves. So microwaves are what we use in your microwave oven in your kitchen. And then radio waves are the last one. So radio waves are the longest. I like to think of radio waves. You can remember that they're the longest because they travel the longest distance, whereas like microwaves, they only travel across your microwave. But a radio wave travels from like Denver to the outskirts of Denver, or sometimes even further than that. So it's a long wave. Okay. Different types of waves. So things look different. What I love about this is there are animals that see with different, not just different colors, but different types of waves than we do. Like bumblebees can see ultraviolet. So this is on the left side of that. That's kind of what a flower looks like to a bumblebee, except for the fact that we're trying to perceive what it would look like to a bee without us having the ability to perceive it. We just, it's not that we can't see it, it's just that we actually can't see it. Human eyes have cones, and we have 3 different types of cones that go for the 3 different types of colors, the red, blues, and the yellows. So those 3 different colors activate the different cones that we have, and it's the wavelength of that color. Once that wavelength, which is tied to a specific energy, hits our cone, it activates our eyes for that color. And combinations of those wavelengths get the combinations of those colors so we can see the whole rainbow. But animals like bumblebees, now some of them, like cats, have 4 cones, but other animals have fewer cones than us. They just have different cones because we have red, green, and yellow. Red, yellow. Wow. Okay. Red, green, and blue. Those are the wavelengths that we have. But different animals have cones that are activated at different wavelengths, at different energies. So we see the flower that's on the right, but a bumblebee would see the flower that, we try to say on the left, but we have no idea, actually. We really can't imagine it because we just don't have the capacity to see those colors. Another application of that is in space. Here's some different electromagnetic views of the sun. So we normally get to see visible light. So that's why that one's omitted, because there's 7 different types of electromagnetic radiation. Visible light's the one that we get to see. So here's putting in a filter of the sun for all of these different things. So radio, micro, infrared, ultraviolet, X-ray, gamma ray, and those are in order of the lowest energy is radio waves, the highest energy is gamma rays. It's just cool to see different things because you can notice there's different spots. Like the ultraviolet, you get this weird looking thing just in the middle of it that you don't see through any of the other filters. Gamma rays, you see this really bright spot on the right that you can kind of see in X-rays, but you can't really see anywhere else. So it gives us access to a whole different way of looking at planetary bodies, to a whole different way of understanding them, other than just look through the telescope. Okay, so more types of waves, and this is kind of tricky because more types of waves typically is broken down into, it's breaking down mechanical waves, but electromagnetic waves kind of fits in to one of these also, kind of. So a transverse wave. Transverse wave is one that you see moving side to side. Longitudinal wave means it goes in and out, so it compresses and then expands, and then it compresses, and then it expands, and then it compresses, and then it expands. So difference between transverse waves and longitudinal waves. The primary reason here, transverse wave is something that's moving, because the energy propagates toward the direction that we are like, oh, okay, the wave goes that way, the wave goes that way. That's the direction of energy propagation. So in our brains, when we see a rope that has a wave moving down it, is the rope actually moving? No, it's just the energy that's moving along the rope. But the rope is moving to the left and then to the right. But then it returns to its original spot. I mean, if you keep making the wave, then it moves to the left, to the right, or up and then down. But then it just stays there. It keeps moving in its initial location. Whereas longitudinal waves, if I have a little particle, it's going to move to the right a little bit to compress into the right side, and then it'll move back to the left a little bit to compress into the left side, then to the right, and then to the left. So the main difference here, transverse waves, movement is perpendicular to energy propagation. So I'm just going to say E for energy. Whereas longitudinal waves, what's different here is that the movement is parallel to the energy propagation. So sound is an example of that. Slinkies are an example of that because you can compress the slinky. Whereas transverse waves are like ocean waves, ripples on water. Electromagnetic waves fall into the category of transverse wave as well. You also have like the wave in a stadium, right? Because you stand up, but the wave isn't traveling up and down. The wave is traveling left to right. You are just moving up to down. So you're moving perpendicular to the energy propagation there. Okay, transverse waves. Oh, and it's a nice GIF. It is a fantastic GIF, and it did not upload into my little system here that I take notes on. I'm going to see if I can paste it over. Can I paste it? Please. Let's try this one more time. Okay, we'll try to paste this over, copy. And if you have your slideshow out on the PowerPoint, you can see this already. You can see the transverse wave. So go ahead and make sure that you can actually see that because it is it's not functioning for me right now on this. But I have one more thing I might be able to try. Sorry, one last thing. Okay, yeah, that won't work. All right, so go ahead and just make sure that you have the slideshow open for you so you can view this as you are going along. So transverse wave, you'll see that on the transverse wave, each one of these particles is just moving back and forth. It's moving back and forth. However, it looks like the wave is moving to the right. Well, that's because the energy is moving to the right, but the particle itself is moving up and down. Each particle is moving up and then down. So these particles have already moved up, they need to move down. These particles have already moved down, they're going to move up. So just track one particle at a time on that little GIF there. All right, so then the other type is longitudinal waves. And the GIF on this one is also absolutely fantastic. So this is the energy is propagating to the right, same thing. And each one of these particles is moving to the right, and then it's moving back to the left. Every one of these is moving to the right and then to the left. And there's a couple of those particles highlighted for you in the GIF that you can track that moving left and right. These words, compression and rarefaction, those are ones that you don't really need to know. Compression is just where the particles are. Rarefaction is where the particles aren't. But you don't need to know that. What you do need to know is that this is just all due to particles collide into particles. And that's how sound works, is right now I am speaking. And sound is when things vibrate. So sound is all about what's wiggling to make that sound get to you. So right now, as I'm speaking, my vocal cords are doing the wiggling, reaching across the space. And so the space between my vocal cords and the computer's microphone, that air is wiggling. They're moving back and forth and compressing into one another until it hits the microphone in the speaker. And then the microphone has something that wiggles back and forth. And at that point, it wiggles a magnet back and forth at that amount of time. And that magnet is inside a coil of wire. Because we've looked at when a magnet's in a coil of wire and it's moving, that creates a moving magnetic field, which turns into current. So just by something wiggling and something moving, that creates that electric current because we have a magnet that's wiggling, creating a changing magnetic field, inducing that current. So that is how, and then you just take the whole reverse of that. It just starts with the wiggling magnet for you to listen to this, and then it goes across the space, hits your ear, gets to your eardrum. That's a wiggling little piece. Then it gets into the cochlear bones and the cochlear fluid that's inside your ears, which eventually gets turned into neural impulses based on wiggling. So it's all about things wiggling when you're getting into sound and longitudinal stuff. But here's the note. You need something to wiggle. Sound cannot exist where there is no medium. Sound can't exist where there is no medium, which means in space, and this is my biggest movie pet peeve, in space, should there be explosions or should there be explosion noises in sci-fi movies in space? Absolutely not, because there is nothing wiggling between where the explosion happens and where you are as the perceiver of that explosion, or at least as the CGI person. There's nothing there. So there should be no noise when you're viewing an explosion in space. Okay, sound in air travels at around 331 meters per second. That is close to 700 miles per hour. It's close. It's not exactly, but it's close. And this gives you a nice little sense of particles bounce. So it's the air molecule moves forward, collides with another particle, bounces back, collides with the backwards particle, moves forward, collides with that particle, over and over and over. However, particle collisions aren't perfectly elastic, which means that it loses energy over time. So eventually, it gets far enough away where the energy is enough lost that you cannot you cannot hear that because the energy is just dissipated before it reaches you. And that's what we call out of earshot. Okay, so then moving forward. Here is an interesting question. In water, sound travels at around 1,500 meters per second. Why? Go ahead and pause the video and postulate. Why do you think so? Make a prediction. Pause the video. Go. So now we can talk about why this happens, because water molecules, they're a lot closer packed together than air molecules are, which means that when it bounces back and forth, it can happen a lot faster because they don't have as much space to go through before the next collision. So water makes sound travel a lot faster than air does. Water waves. Now, earlier I said that they were transverse waves, and this is a little bit true, but it's not quite true. It's hard to um, it's hard to see or AP doesn't really ask about this because it truly is both. You don't really have to know too much about it, but it is kind of interesting to watch the circle happen as these molecules are moving around. Again, here's a good GIF that I can't show on my note taking platform here. So make sure you have the PowerPoint pulled up and you're following along so you can see that GIF as it's going through. All right, so here now is a good little image here to talk about longitudinal waves, transverse waves. Now the top is longitudinal, bottom is transverse. You don't have to know the letters, the P waves and the S wave. You don't have to know those. If you're interested in the geosciences, right, earth science, this does correlate to earthquakes. Because in earthquakes, there's P waves and there's S waves, and one of them happens faster, the other happens slower. Take a moment and think which one happens faster, which one happens slower. And the faster one is P waves because there's a lot of matter in Earth, so it's kind of like sound. They collide into the next particle very quickly, so that propagates well. Whereas S waves, the whole Earth kind of has to raise up a little bit and then get lowered down, and then raise up and then get lowered down. So it travels less quickly when that happens, as opposed to just a molecule collides into the next when they're closely packed together. All right, parts of a wave. So here's some important variables that you need to know. The Greek letter lambda is wavelength, and that's from peak to peak is what we say. You could also say trough to trough. It is the exact same thing as if you're looking at the wavelength of a sine wave of from one point on one wave to the same point the next time it happens. So if I'm looking at the zeros, notice how it's the zero while the wave is moving down. So not here because that's a zero while our slope is positive. We have to come again to the same point. So zero with a negative slope, same thing has to happen, zero with the negative slope. So that's also an example of a wavelength. However, it's easiest to find it just based on the graph that they give you. Amplitude is from the midline to the peak. Crests are the top, troughs are the bottom. The zeros here are nothing. It's a zero. Okay, so there's that. Here's some questions for you. What is the difference? So pause the video. On the left screen, what's the difference between blue and red? Right side, what's the difference between blue and red? Pause it here. And on the left, the blue wave has a greater amplitude. The red wave on the right has a greater wavelength. But on the right, a greater wavelength means a smaller frequency. If it's longer, it happens less often. So just remember that those are inverse of each other. Okay, how many wavelengths in each one of these? Well, pause the video, figure out how many wavelengths in each of those. Go. And the answers, so you have 1, 1.5, 2, and then the bottom one is 3.5 wavelengths in that. So you have to be able to identify how many wavelengths are happening. Okay, the next term here, period and frequency. So period is time per revolution. Frequency is revolutions per time, so they're exactly opposite of each other. This is my equation that I have here, and I believe AP gives this one to you as well. So you have period and you have frequency, and it even relates in there omega, right? Remember, that is angular velocity. So that's essentially how quickly is it rotating through a cycle, because we get one cycle, and in a sine wave, one cycle happens in 2 pi, right? In 2 pi radians, that's a sine wave. So if you have your sine wave there, that's the cycle. Omega, that is your angular speed. Essentially, this is the amount of time that it takes, and that's how fast you're going through it. So time over that, or I'm sorry, this is your distance. It's kind of like your angular distance, velocity, time, and then remembering that. You can also do 1 over frequency to get the period, or you can do 1 over period to get the frequency as well. And looking at this on AP's equation sheet, I'm just looking for this here. They give this to you. It is in the equation sheet. It's actually under the mechanics section. It's under the mechanics section. So all the stuff that we did last year in AP 1, it's right with the period of a spring and the period of a pendulum oscillation. So it's in that mechanics section as opposed to being in the waves and optics section. So make sure you don't lose it. So make sure that you can rearrange these angular speed to get 2 pi f. Make sure that 2 pi, or because f is in seconds, f is in 1 over seconds, or hertz, hz. And yes, there's a lot of jokes to be made there, and I will be making those jokes, so don't you worry. All right, we have ourselves a practice question here. Oh, did I go too far? No, it gives us the answer. If a period of a wave is 2 seconds, what's the frequency? Well, remember that period is 1 over frequency, which also tells us then that frequency is 1 over period, so we can get 1/2, and the units is hertz, which turns into a 0.5. Okay, there's just a little bit of practice on that one. What are the period and frequency of this wave? And it gives it to you right away. So try to not cheat. Period and frequency of this wave. Well, period, essentially, right, it's from one instance of it happening to the next instance of it happening. So I picked 0 with an upward slope to the next 0 with an upward slope, and that happens at 8 seconds, and it happens at 16 seconds. So I'm going to say it's an 8-second period. Frequency is 1 over period, so you just take 1/8. Which gives you that 0.125 hertz. Another graph, calculate frequency and period. So frequency is how often it happens, right? It's how many times it happens per second. So we can see from the graph that there's 1.5 cycles, right? It goes from 0 at up to 0 moving down, and that's through 1 full cycle there, so 1.5 cycles. And that happens in 16 seconds. And those are the numbers I picked off the graph, because if I look here, it's between 10 and 11, or 10 and 12, but it's not quite 11. So I'm not going to get a very accurate number if I take that point. What AP does is they will always give you 2 points that are nice data points. They'll always give you 2 of them. Always one will be on the left side of the graph. Always one will be on the right side of the graph. So pick the nice data points, and then just say how many seconds per how many revolutions. There's your period. All right, seconds per revolution. There's your period. And then you can just invert it, revolutions per second, and there's your frequency. So we get 10.7 seconds, and we get 0.094 hertz is our frequency. All right, not too much more to go here. Speed of a wave. So the speed of a wave, right? Velocity is displacement over time. So that would be then lambda is our displacement. That's how far a wave has to go. And then period is how long it takes to get from there to there. So distance over time. But then remember, 1 over period turns into frequency. All this equation does is it rearranges, divides both sides by frequency. So you get lambda is equal to V over F, since we divide by frequency. This is what AP gives you. So this, as your equation here, this is now in the optics and waves section of the equation sheet. So it's where you want it to be. It's where you expect it to be. We've got 2 last practice problems here. So one practice problem here, light propagates through a medium, not a medium, through the vacuum of space. at a speed of c is 3 times 10 to the 8th meters per second. And that is a value. That is a constant. That's on the top of your equation sheet. You've got to know 3 times 10 to the 8th, 3e8 meters per second. That is the speed of light. I mean, you don't have to memorize it because you're given it as a constant, but you do have to know that that is a constant. Light through the vacuum of space. What is the frequency of a gamma wave if it has a wavelength of 2.5 times 10 to the minus 13 meters? Okay, minus 13, first of all, just recognize that is tiny. That is absolutely tiny. So gamma waves are tiny. Okay, so then with this, we can say, using our equation, wavelength is equal to velocity over frequency. Well, we're asked, what is the frequency? We're given the wavelength. So wavelength is 2.5 times 10 to the minus 13 meters. Velocity of light is 3 times 10 to the 8th meters per second. We don't know our frequency. Okay, so you solve for F. Frequency. And in this case, we get a frequency of 1.2 times 10 to the 21 hertz. So that is oscillating at 1.2. Let's see, how many times would that be? I think that's 1.2 hexillion times every second. That's a lot. That is a lot. So that gamma waves are incredibly high energy because it's oscillating back and forth so gosh darn quickly. Okay. To kind of put this in perspective, a gamma wave is it's approximately the distance from a proton to the electron of that atom. So it's about the size of half an atom is a gamma wave, if not even smaller for a lot of them. So just know that. Okay, so there's our answer again. Last practice problem. Go ahead and pause the video, read this question, try it out. Which of the following correctly ranks the wavelength and speed of microwaves, radio waves, and X-rays in a vacuum? Well, speed of light, it doesn't matter what kind of light it is. It matters that it is light. And micro, X-rays, and radio waves, those are all light. They're all electromagnetic radiation, so they all have to be at the same speed. So all of a sudden we can cross out these two because they have to be at the same speed. Now we just have to do wavelength. Well, you have to remember that gamma is the shortest wavelength, highest energy, then X-ray, then UV, then visible, then infrared, then microwaves, then radio waves. You've got to know the order of that because they will not ever give it to you. You have to have that memorized. I know I hate saying that word, but here we go. So we're looking at wavelengths, making sure that we know that radio waves are the longest. So all of a sudden, based on that, now we can say that it is option B. Honestly, for this question, you didn't even have to have them memorized. You just had to say, oh, wavelengths aren't the same. Because if speed was the same and wavelength was the same, then frequency would be the same. But that's not true because that would not give us enough information to have a different wave. All right, so there's our last slide here. So the major takeaways from this, just generally speaking, electromagnetic versus mechanical waves. And then transverse versus longitudinal waves. Other takeaways, takeaways, I didn't even mean to do that. That was just a slip of the tongue. Other takeaways from this, make sure you know the order of the types of waves that are listed at the top of this. So you will also have to kind of have a comparison. You'll have to have a comparison for these. And this is something that I do already have kind of created for you here for a lot of these waves, for the ones that you have to know. So let me just plop this on a new kind of a slide here. Um, so the comparisons of the length, because AP does expect you to know these, and they expect you to know these exact comparisons. So gamma waves are smaller than an atom. X-rays are approximately the size of an atom. That's how X-rays can measure the atoms in our body, is because things can measure stuff that's the same size as it. It's really good at measuring that. Infrared is approximately the tip of your pencil. Microwaves are about the size of a coin. It's a centimeter or two. Radio waves, you can compare that to a football field. Really, it's anywhere from like the length of your desk to a football field, anywhere that's like 1.5 or 2 meters. And larger is a radio wave. But these are the ones that AP wants you to memorize. And yes, I did say memorize. I know. If you have questions on that, let me know. I do have a whole set of flashcards for you to do on these, and I will provide that list. So if you have any questions, let me know. But otherwise, that'll do it for this video. Hope you have a great rest of your day, and we will see you next time.